Yes, now it is fine. Okay, 5 minutes we can close it. Yes, a very good morning to all of you. Am I audible and visible to everyone? Yes. Very good morning to all of you. And see, today we are going to finish off. Yes, you can say that whoever is asking me, Z effective is directly proportional. Yes, higher is the Z effective, higher is going to be force of attraction on the electron which you want to take out. Okay, so that is the reason it is going to be higher and directly proportional, you can say. Okay, so today I'm saying that we'll be able to finish off this particular chapter, right? And new chapter will be starting from the new day. Okay, is that okay with everyone? So we are almost towards the end. I didn't say inversely proportional. Maybe beta you have written it wrong. Kindly check it. Okay. Fine. Without any further delay, let us start off with this session. Okay. Fine. It's okay. So now next property, I think we have finished off with the electronegativity, right? Now today we are going to learn whichever is, I think we have studied about Z effective, atomic radius, ionic radius. Then we went for ionization energy. We went for electron affinity, electronegativity. And now we are going for this one, seventh property, which is nature of oxides. Nature of oxides. So basically, a compound of different elements with oxygen is only known as oxides. Okay. Now, when it comes to types of oxides, right, we are supposed to know that there are basically four categories. One is neutral, another one is acidic, another is basic, and one more category which is amphoteric oxide. Okay. Now, from the name, you must understand when I say neutral, that means they neither react with acid nor they react with base. That's how they are neutral. Okay. So, I'm saying that do not or else neither react with acid nor with base. Neither react with acid nor with base. Now, acidic oxide, that means what? Acidic oxide. Acidic oxide means their solution in water is going to be acidic, right? So, their solution in water is acidic. And if they are acidic, they are going to react with base. So, I'll write down they react with base. What about basic? When you put them in waters, for example, if at all I am talking about acidic, no. For example, if at all I take, suppose this one is there. SO3 you take, suppose, hai na? So if at all I put this in water, so it forms H2SO4. Hai na? So what I've done, SO3 plus H2O, we have got H2SO4. And generally non-metallic oxides are acidic. Hai na? I'll give you a list, do not worry about that. But at present, in general, I'm just taking one example. Okay. Now here, their solution is basic in water. And definitely they are going to react with acid. They react with acid. For example, if I consider Na2O plus water, I'm going to get twice of NaOH. So it is basic solution. You know that NaOH is a strong base. So normally metallic oxides, they'll be like basic in nature. Acidic, non-metallic oxide, they are acidic. Okay. Now, amphoteric, they react both with acid as well as base. That's what is amphoteric oxide. Okay. So first you have this particular, note down this and then we'll proceed further. Okay. I'll give you the list of all those things here. Amphoteric oxide, neutral, and then you should have a general idea. And if you want to write here, you can easily write down that generally non-metallic oxides are acidic. And we are writing generally, okay? And here we are writing generally metallic oxides are basic. Yes, hopefully people have written this. Okay. Now let us write down something here. Suppose I want to give, you must remember what are the neutral oxides. There are only three: CO, NO, N2O. Right? These are the three neutral oxides. Second one, you are having amphoteric oxides. Okay. So amphoteric oxides, for that I'll give you a trick here. So basically it is Prabhas, you know, Allu Arjun, everybody knows, you know, famous stars here. Bet, you know. Sunny Deol is like veteran actor in Bollywood, right? Bet Sunny Deol in car 3 times so that you remember what is the charge. And then they like Gajni, you can remember, like Gajni, right? And so what I want to say is oxides. Their oxides are amphoteric, right? Whatever the oxides you have, like for example Pb, you are having PbO and PbO2, right? So I'm writing PbO, PbO2, right? They are amphoteric, you know? You are having SNO, SNO2, right? And here I have taken two, you know, kind of these two actors which you already associate with Prabhas, you know? Now everybody knows him, okay? Allu Arjun also. So bet, you know, they have basically beaten Sunny Deol. Actually, they called him in a car, right? And what they did, they bet him, both of them. You know? Sunny Deol normally he is known for his kind of, you know, a kind of masculine personality, or else you can say that in whatever, like wherever there is a fight scene, he'll be visible. You know? In the old films, I'm saying, okay. So here you can remember that, okay, Sunny Deol, right? And he was beaten by these two fellow in the car, and how many times? 3. And they acted as if they have not done anything, you know, like Gajni, you know, only 15 minutes memory. So you can remember like that, okay? SNO, SNO2, you are having Al2O3, you are having Ga2O3, right? You are having beryllium oxide, okay? You are having Cr2O3. See, the thing is, you must remember it is Cr plus 3 only, okay? And one more thing I have to write down. This one you already know, okay? And you are having here Ga2O3, we have already written. Then you are having ZNO, right? Now, when I was talking about this amphoteric oxide, I am saying that they are able to react with acid as well as bases, right? So, if at all I am having ZNO plus HCl, it will be forming ZnCl2 plus water, salt plus water, ZNO plus NaOH, it will be able to form Na2ZnO2 plus water, right? So this is also another salt, okay? So this is sodium zincate, this is zinc chloride there, okay? So you are able to see that this ZNO, it was able to react with acid. So at that time it behaved as a base. And when it is able to react with the base, that means it is acting as acid. So basically it will be able to react with both of them. Okay. Now here there is one more point for amphoteric oxides. Metals in +4 oxidation state in their oxide are amphoteric, except VO2. Here vanadium, है ना, +4. This is basically basic. So do remember that. Please write this down, then we'll proceed further. Neutral oxide I have written above. If you're not able to relate with this Sunny Deol, you can also switch to Sanjay Dutt. And everybody knows him. He was in their KGF 2 movie, right? So whichever, I just want you to remember the element, that's all. So SN, here also it was SN, tin. I hope we are done writing this. Then next point, I'm going to write down oxides of metal. You must remember, if they are in +1, +2, +3, that means metal is in +1, +2, +3 oxidation state. It is going to be basic. If the metal in those oxide is in +4, it is going to be amphoteric. And do remember, I'm not talking about VO2 here. Whichever is the exception which is covered in that particular, amphoteric trick, that is already, kind of excluded from here. Then +5, +6, +7, they are going to be acidic. Okay. So do remember here, again I'll write down here, this is except VO2, so that you don't, kind of repeat the mistake. Okay. Now, next is oxides of non-metal. They are acidic except neutral oxides, है ना? Neutral oxides, CO, NO and N2O. Getting it? So normally if you see any non-metal, its oxide is going to be acidic, but do check, are they them? CO, NO, N2O, right? Then similarly, you are having oxides of metalloids, right? In that case, I am saying they are generally acidic except As plus 3 and Sb plus 3. Their oxides are amphoteric. Right. Achha, one more thing you can include here. I think I have written here. Okay. You can remember vanadium plus 5. Okay. And you are having basically here Sb plus 3, As plus 3. Here also you can write down they are oxides. Oxides of Sb plus 3, As plus 3, they are also amphoteric. You can include this point. Written? Okay. Write down this one. And after that, we'll proceed further. Hopefully we have written that. Then we can proceed further. You can include +5 also here, right? So that you don't get confused. See here, you can remember like this. Vanadium in +5. So this is Roman letter 5, right? And in that fifth, like now you consider 15th group element Sb and you are having arsenic. They are in +3 oxidation state. They are also amphoteric. Okay. So remember this entire trick, and what you are having is V +5 also, right? And V, you take it as a Roman number letter, vanadium, right? You consider it for remembering the other two. They are in their +3 oxidation state. So their oxides are also amphoteric. V2O5, Sb2O3, right? Like that. Okay, I hope this is written. Now let us go for trends of the nature of oxide in periodic table. Now here we remember acidic nature of oxide, hydroxide, or else the oxy acid, that is directly proportional to, we can write down the electronegativity, or else Z effective, or else we can write down non-metallic character, right? We can associate with this non-metallic nature. Okay. So basically, if at all you are having a non-metal, suppose we have taken carbon dioxide. So when I put that in water, I'm getting H2CO3, right? So that is a non-metallic oxide. Okay. So non-metallic oxide, they are going to be acidic in nature. So we just have to consider, and definitely you can relate the non-metallic nature with the electronegativity also. Because electronegativity, if it increases, so the tendency to attract electron increases, no. So non-metallic nature increases, and non-metallic nature increases means acidic strength increases. I hope this is clear. Hydroxide, oxide and hydroxide, and oxy acid is what? You'll have definitely oxygen and hydrogen there, and along with that you'll have a non-metal. That's what is the definition of oxy acid, right? Even your H2SO4, if you think, so you're having OH and you are having a non-metal there, which is sulfur. Okay. Now in a period, let us see how it happens. So in a period, when we are moving from left to right, okay, so what we are saying is non-metallic nature increases. If non-metallic nature increases, that means what? Acidic nature of the oxides, that increases. Okay. Similarly, in a group, what happens? In a group, top to bottom, we are saying that the metallic character increases, no? It becomes more easier to lose electrons rather than to gain electrons, right? So metallic nature, that increases, because in general we say, no, electronegativity decreases, so electropositivity is going to increase, and always these two things are inversely related. So electronegativity decreases and electropositivity increases, and when I talk about electropositivity, that means it is the characteristic of a metal. Okay, so that's how we say that the metallic nature is increasing. So if metallic nature is increasing, then basic nature of oxides, that will increase. And what about acidic nature? It will be reverse. So acidic nature of the oxides, it is going to decrease. Is this clear to everyone? So make sure that you are writing this. This I'll scroll up a little bit here now. And then we'll see some questions here, okay? Yes, are we done writing? Okay. Now let me give you one question, first a simple one. Identify the nature of given oxides. This is just to, kind of make you thorough with whatever I have written. Okay. That means about the nature of the oxide which I discussed. Neutral and amphoteric you remember clearly, right? Okay. So I'm going to write down, you just have to identify which one is neutral, which one is basic, which one is acidic, and which one is amphoteric. Okay. So I'm giving you 2 minutes, please sort them out. So first of all, you must, able to identify from the group which one is kind of, neutral. You just remember two of them, neutral and amphoteric. Okay. Rest you know that for metal, you just check for any metal if at all it is given to you. Now you should be comfortable, identifying whether a particular species is metal, non-metal or a metalloid, right? That has already been taught and it is expected out of you. So when you're going for a metal, for a particular oxide, if you think it is a metal oxide, then you just check whether this metal is coming under that trick. That trick was Prabhas and Arjun bet Sanjay Dutt in car 3 times and forgot about it like as if they are Gajni, right? So if it is part of that, or else the metal is in +4 oxidation state, right? Or else it is As +3, Sb +3 or vanadium +5, they are all going to be amphoteric. Apart from that, if there is like +5, +6, +7, then you are having acidic, okay? I'll give you one more. So for basic you write down B, for acidic you write down A, for amphoteric you write down AM, and for neutral you can write N. MgO, metal oxide, this is not part of that particular, just now the trick of amphoteric. So this is going to be basic because it is in +2. PbO, Prabhas, right? So it came, so it is like amphoteric. V2O5, +5, so this is amphoteric. Chromium, again it is part of that trick, it is amphoteric. Mn is in +7 oxidation state. +7. Remember metals in +5, +6, +7. They are acidic. N2O5. It is a non-metal. Non-metal. This non-metal, for non-metal, whenever you encounter the oxides of non-metal, you just check whether this non-metal oxide is belonging to that neutral ones or not. Neutral ones means you are having N2O, NO and CO. If it is not, then straight away you can put this as acidic. As2SO3, this is amphoteric. +5, what it is going to be? It is going to be acidic, right? B2O3, non-metal oxide, again acidic. VO2 +4, but remember this was exception. So this is basic. Ideally it should be, what it should be? It should be ideally amphoteric because metal is in +4. But what we are going to write down, since it was like in the exception, V +4, it is basic. And this is neutral. MnO2 you are having in +4. This is going to be amphoteric. So like that way we identify. Hope it is correct. Now next one, arrange the following. Arrange the following in decreasing order of their acidic strength. First one, B2O3, CO2, N2O5. Second, this you have to do. Cl2O7, SO3, P4O10, SiO2, Al2O3, MgO. Then CO and CO2. Then you are having, suppose, PbO and PbO2, N2O5, P2O5, Li2O, Na2O, K2O, Rb2O. Then you can have FeO, Fe2O3. Then you can have MnO, Mn2O3, MnO2, Mn2O7. Okay, do these questions, then we'll discuss them. As such, they are simple questions only. And for this question, I'm giving you a hint, or else wherever you are having similar element. So, higher is the oxidation state of the element, higher will be the acidic nature. Right? Are you able to understand this? We have already written higher oxidation state means then it is able to kind of attract the electrons, or else its electronegativity you can think that it is more, and hence non-metallic character more, so it is going to be acidic. So when it comes to Li2O, so you are going along a period. So along a period, non-metallic nature, that is increasing. So what is going to happen to the acidic nature? It will increase. Getting it? What about this? Again, when you're moving from left to right, you will see that the non-metallic nature is going to increase. Right? This is amphoteric, and after that it is like non-metallic character, acidic nature is beginning, and here it is basic. Among CO and CO2, it is +2, it is +4. Higher oxidation state, more acidic. +4, +2, this is more acidic. Right? N2O5, P2O5, down the group acidic nature decreases. Down the group acidic nature is going to decrease and basic nature is going to increase. FeO and Fe2O3, this is +2, +3. Right? Here it is +7, +4, +3, +2. I'm just asking you the order of acidic nature. Okay. Definitely some of them, they are going to be amphoteric here. Right? Need not worry about it. We are just comparing the acidic nature. Getting it? Hope it is clear to all of you. So make a note of it. Yes, I hope it is done. So with this, we finish up the nature of oxides. Now I think the next one is valency. So when I talk about valency, basically what is valency here? Valency is the combining capacity of any element. When I say combining capacity, so that means you have seen different elements, they combine to form a molecule or a compound, right? So either they lose certain number of electrons, or else they gain certain number of electrons, or else they share certain number of electrons. So that's what is the valency. How many number of valence electrons they are able to lose or gain, right, to form a particular molecule or a compound there, right? So here I am writing this one as it is the number of, or else it is the combining capacity. It is the combining capacity of an element. Okay, and we can also say it is the number of electrons gained or lost by an atom, or by an atom of an element. Okay, now let us say if at all for metals we say valency is equal to number of valence electrons itself, right? And for non-metals, we say that the valency is equal to 8 minus the number of valence electrons, right? And for noble gases or inert gases, they do not tend to combine and lose or gain electron. So valency we are going to consider it to be 0. So for example, I am writing different groups here. Group number, valence electrons, and we are going to write down the valency. Okay. So here you are having 1, 2, 13, 14, 15, 16, 17 and 18. How many number of valence electrons? 1, 2 here, 3 here, 4, 5, 6, 7 and 8. What is the valency? These two are basically metals. Here you are finding non-metals. And this is basically inert gases. So for inert gases, I can say they are not going to react. They are not going to lose or gain electron. Here valency is 1. Here valency is 2. Valency is equal to number of valence electrons. For this one, right, up to 4 basically. For non-metals, if at all number of valence electrons is like less than or equal to 4, then in that case, valency is equal to number of valence electrons itself. Are you getting it? For non-metals I have written, if the number of valence electrons is less than or equal to 4, in that case the valency is equal to number of valence electrons. If they are greater than 4, in that case you apply 8 minus number of valence electrons, right? So here it will be 3, here it is going to be 4. Now the valence electrons in the non-metals are more than 4. This one you are applying for number of valence electrons greater than 4, right? Now the thing is, for this one, 8 minus 5, you will be writing 3, 8 minus 6, 2, 8 minus 7, 1. So you can understand group 15, if they accept 3 electrons, so they will achieve that noble configuration. Here, if they accept 2 electrons, then they are going to achieve that noble gas electronic configuration. Similarly, group 17, if they accept 1 electron, they are going to attain that. So that's what is the valency. Clear about this? So please write this, then we'll proceed further. And for D block elements, we are not writing because D block elements, they are going to show variable oxidation state. Okay, because they can lose their Ns electrons and as well as N-1 D electrons also. So we are just looking at basically the trends in S and P. Yes, I hope people have written this. Then now let us, I think we are done with all the properties here, and we can do one thing. We can write down for the oxidation state as such. You can put a note here. Oxidation state. So if it is group 1, then the oxidation state which is, it is always +1. Group 2, it is basically +2. Now the thing is, we are talking about P block, right? So in P block, basically, I'll write down one statement here so that it becomes easier for you. For P block, right, maximum oxidation number or oxidation state, that is equal to IUPAC group number, which we write now 1 to 18 minus 10, and minimum oxidation state is equal to IUPAC group number minus 18. That way you do, okay? That is IUPAC group number minus 18. So let us see if at all I am talking about group 13, right? So maximum oxidation number is going to be 13. That is basically 13 is the group number minus 10, which is +3. And minimum oxidation number here is going to be 13 minus 18, you can think of -5, right? Similarly, group 14, so group 14 you will be having maximum oxidation number as 14 minus 10, which is +4. Minimum oxidation number you will be having 14 minus 18, which is -4. So basically, if at all I go on writing group 15, so for group 15, maximum oxidation number is 15 minus 10, which is +5, and minimum oxidation number is 15 minus 18, which is -3. Getting it? So basically, group 15, you know that nitrogen, you can find the compounds existing. Whenever I am finding minimum and maximum, that means suppose if at all I talk about nitrogen, so you can easily find out the compound of nitrogen ranging from -3 oxidation state to +5, right? So you'll have 0 also, you'll have +5 already, you have +4 also, +3 also, right? Getting it? So I'm not writing further for the rest of the groups because it is understood. I've given you for the P block, okay? S block and P block we are talking about. Yes, I hope everyone has written that. Please finish writing it. Yes, I have not written further for group 16 or 17 or 18. It is understood. Once you finish writing, please do thumbs up so that I can understand that. Okay, good. Now, next, I think all the atomic properties are done here. Now, we are going to just learn few things which are remaining here, okay? Which is like small things which you must know. One is inert pair effect, diagonal relationship, and the anomalous behavior, okay, of the second period element. So those are all small topics. Now when I talk about inert pair effect, so let us just focus on group 13, group 14 and group 15, right? So the elements here are boron, aluminium, gallium, indium and thallium. Here it is carbon, silicon, germanium, Sn and Pb. Here it is nitrogen, phosphorus, arsenic, antimony and bismuth, right? Now here what is seen normally for group 13, like maximum oxidation state which is stable, it is +3, right? Here it is +4 and here it is +5. But what is seen that basically this is belonging to what? This is belonging to second period. So this will be third, fourth, fifth, and sixth. This is sixth period. Okay. And when I say sixth period, so in the sixth period, n equal to 6, you will have also 6s, 4f, right? 4f filling will be there, right? 5d filling will be there, and you will be having 6p filling, right? Are you able to understand that? In the periodic table, when I write n equal to 6, so basically you will be having 6s first of all getting filled up. After that, you are having 4f getting filled up. No? You remember lanthanum. Lanthanum will be 5d1, and after that cerium to lutetium. So 14 electrons are getting filled up there. And then you'll be having 5d10 complete, and then you are having 6p6, right? So we are interested in this, right? Now what is seen here is, as you proceed down the group, rather than that stability of +3 oxidation state, in case of group 13, it decreases, right? That means what? I'm able to see thallium +1 more stable as compared to thallium +3. That means, suppose if at all I'm writing here, let me compare gallium, indium, and thallium. So somebody is asking me about the stability of this, right? So in that case, I'll be able to say that the stability decreases, right? If at all I write gallium +1, indium +1, thallium +1, so I'll be able to say the stability like this. Are you able to realize there is a difference of 2 here? Okay. Similarly, if at all I write down for group 14, stability over here is, you are having germanium +4, Sn +4, and Pb +4. I can also write down for germanium +2, Sn +2, and Pb +2. Here by mistake I have written +2, make it +4. So stability of +4 decreases and the stability of +2 increases. Now if at all I see the similar thing for this also, stability here for +5 decreases down the group. As +5, you are having Sb +5, you are having Bi +5. Like this, stability decreases. And the stability of lower oxidation state, just the difference of 2, that increases. Right? So this lower oxidation state stability, that is increasing. That's what is inert pair effect. Hai na? And let us try to understand that with the help of basically your thallium. Right? So you first write this down and then we'll proceed further. And here also you must be clear that if at all I am talking about stability of Ga +3, Ga +1. So it is +3 which is more stable. Indium +3, indium +1. This is more stable. Then if at all I am talking about thallium +3 and thallium +1, it is going to be reverse. Are you getting it? Stability. And I'm not writing for rest of them. It is the similar kind of pattern here also. So please make a note of it, then we'll proceed further. And I hope everybody has written the heading, which is inert pair effect. And mind well, I didn't explain you anything more here. I just explained that basically when you're coming down the group, the stability of the lower oxidation state, that means the highest oxidation state -2 is becoming more stable in case of group 13, 14 and 15, which you are able to see. First make a note of it. Yes, I hope it is written. I'll scroll it up a little bit. Here also similar trend is there. Okay, if at all I am writing stability of Ge +4 and Ge +2, it will be Ge +4 which is more stable, right? Only in case of Pb it is +2 more stable than Pb +4. Okay. Now let us try to understand the case of thallium, which is 81. When you write down the electronic configuration, it is xenon, right? This is 54, right? Then it marks the ending of 5th period. So you are moving on to 6th period. 6s2, 4f14, 5d10, and you'll be having 6p1, right? If I arrange it shell wise, that means it's going to be 4f14, 5d10, 6s2, 6p1. Right? Now I'm making you understand what is this inert pair effect. Okay. Why the stability of +1, it is increasing more down the group. So suppose this is nucleus, right? And I'm showing this is 4th shell, 5th shell and 6th shell. Here you are having 6s6p. There are 2 electrons, 1 electron here. This is 5d10. This is 4f14. Right? So what is happening here is after the filling of 6s electrons, the electrons are progressively being filled up in 4f, right? So can I say that as 14 electrons filled up there, so there will be like corresponding to that 14 protons also present here, right? Now what happens is because of this increased number of protons, right? What will happen? There will be increased nuclear force of attraction, right? Understood. At present, are you able to follow that? What I'm saying is the electrons are being progressively filled up in the inner shell, which is 4f, right? So 4f, as you see that there are 14 electrons, so corresponding to that, there will be 14 protons, then only it is electrically neutral, right? Now, because of that increased number of protons, what is going to happen? Increased force of attraction, right? But the thing is, you already know that 4f is not able to shield this nuclear force of attraction because it is having very poor shielding effect. So what will happen? This nuclear force of attraction is going to reach up to 5d. And 5d is also like a cousin of him. Because the thing is, if poor shielding of f is there, then similar effect is of 5d, but relatively better. But that is also poor only, we say. If this is very poor, then this is poor, right? So what is happening now? This nuclear force of attraction is reaching on to 6s and 6p electrons. Okay. Now the thing is, out of 6s and 6p, which one is having higher penetration effect? That means which one is more closer to the nucleus? We have studied about ns and np. Out of that, it is ns, right? So that means 6s electrons are relatively more closer. This particular subshell is more closer as compared to 6p, right? So if at all it is more closer, it is going to have more nuclear force of attraction as compared to 6p. So what is the impact now? Here relatively, I'm just talking on relative term. So here relatively less nuclear force of attraction. So I'll be able to remove 1 electron from here. That means thallium has lost 1 electron, right? Now the thing is, if at all I have to remove these 2 electrons of S, which are under high nuclear force of attraction, so what will happen? I need to supply more energy to it. And if I am supplying more energy to it, that means I am supplying the more energy to the system and I am making it unstable. And nobody wants to become unstable. That is the reason thallium +1 exists, right? Now let us try to understand that term, which is inert pair. Pair means 2, right? Now, if at all, in case of thallium, if at all I see 6s2, right? And you are having 6p. If I want it to like form 3 bonds, so what I should have? I should excite one of the electron here now. I should have unpaired electron like that, right? So for doing the excitation also energy is required. Yes. Now the thing is, you already know that basically here there is strong nuclear force of attraction. So for doing the excitation also, I need to provide more amount of energy. And again, more amount of energy, that means what? Making the system unstable. So here you will see that this thallium, 6s electrons, 2 electrons of 6s, they are showing inertness towards bonding. They are not participating in bonding because to make 3 bond, I should have 3 unpaired electrons here. Getting it? So that's what is inert pair effect. Inert because they do not want to form bond. Pair, how many are there? 2 such electrons. Okay. So I'll just write down in 6th period, due to poor shielding effect of 4f subshell electrons, the stability of lower oxidation state. When I say lower oxidation state, that means maximum oxidation state -2 increases, this effect is known as inert pair effect. Okay. Please write this. And once you finish writing, please do the thumbs up over there. I hope we are done writing. Okay. So we can also write the impact of this, that is thallium +3. You are having lead after that, which is in Pb +4. You are having bismuth +5, right? They act as oxidizing agent. Why they act as oxidizing agent? Because they'll oxidize others and take the electrons so that they can convert into Bi +5 to +3, Pb +4 to +2, thallium +3 to thallium +1. Getting it? Act as oxidizing agent. And if at all I am writing thallium +1, Pb +2, Bi +3, they'll be acting as So basically, why they are acting as an oxidizing agent? Because thallium +3, it will accept 2 electrons to get into thallium +1 form. Pb +4, it would love to accept 2 electrons to form Pb +2. Similarly, Bi +5, it loves to accept 2 electrons to form Bi +3. You know? They are able to maintain their highest possible oxidation state only if they are present with the most electronegative elements like oxygen and fluorine. Getting it? That means it's not the case that BiFi does not exist +5. It will exist because it is present with the most electronegative element. Right? Clear about this? Make sure you are writing this. So with this, we finish off the inert pair effect. So I'm just teaching you some of the, small topics which are still kind of important as far as your this particular periodic chapter is concerned. This effect will already be seen, maybe seen later on in some other chapters also. Like when you go for reading your P. So definitely all these things are just a part of it. See, the thing is, you don't think here TLI3 as this one as TL plus 3 and I minus 1. Like this, it will not exist. I told you, no, TL plus 3, it wants to go to the TL plus 1. So what it will do, it will basically oxidize this I minus. That's what is being done. So when I minus get oxidized, it will be releasing 2 electrons. And who is going to accept those 2 electrons? Thallium plus 3, right? So just now we have seen that this will act as an oxidizing agent. So it is going to oxidize I minus to I2 and itself it will get reduced. Now that's what is the definition of an oxidizing agent. Now whatever is I2 which is formed, it will react with some of the I minus which is there and form I3 minus. So in this form it will be existing. Getting it? Now understood? Now fine? So write this down. So these are like some of the applications which are associated with inert pair effect. Can we proceed further? Okay. Now let us go for diagonal relationship. So basically, if at all I'm writing second period elements here. So lithium, beryllium, boron. Third period element, sodium, magnesium, aluminium and silicon. So you are able to see there is a diagonal relationship which exists like this. Diagonally, lithium, magnesium, they are having diagonal relationship. Okay. So this diagonal relationship is due to similar size of them, right? And here due to similar charge to radius ratio, right? And when I'm talking about similar charge to radius ratio, that means I'm talking about B plus 2 and Al plus 3 here, right? So basically, now we have already analyzed all the atomic properties and their trends. So somewhere you are able to see that the elements, they'll be showing the similarity, if at all they're having some kind of, similarity in their sizes, right? So here we are able to see that there are similarity in their properties. Lithium as such, the first member, they're always differing from the other members of their group, right? That is the reason we are not calling them as typical elements. We call this one as typical elements, right? So basically lithium, if you remember, Li2CO3, when you used to heat it, it used to get decomposed and releasing Li2O and this, just like the way MgCO3 does. You are having MgO plus CO2. Whereas all the group 1 metal carbonates except lithium, they are thermally stable. They will not decompose on heating. They'll melt away, but they'll not decompose into different compounds. Getting it? So similarly, beryllium and aluminium, they also show the similarity, right? So because of this diagonal relationship, many of their properties are similar. Getting it? And first of all, why is that diagonal relationship there? For lithium and magnesium, it's basically the similarity in their atomic and ionic sizes. And when it comes to beryllium and aluminium, there is similarity in their charge to radius ratio. And when I am referring to charge to radius ratio, I am comparing B plus 2 charge to the size of it. Al plus 3 charge and the size of it. Please write this down. Yes, I hope it is done. Okay, good. Now, let us just go for the last topic here, which is anomalous behavior of second period elements. So when I talk about anomalous behavior means which is not expected, है ना? They are not showing, they're deviating from their behavior there. Okay. So basically you will understand why they are like, suppose if I say beryllium, है ना? So beryllium, most of its compound, they are covalent in nature. It can maximum for 4 bonds, right? Whereas rest of the members, they can expand their octet, right? So basically, are you able to understand like these second period elements, right? These are very small. Because of that small size, their electronegativity is very high, right? And because of that also, there are many properties which are differing for them as compared to rest of them, okay? So this is due to extremely small size, high electronegativity, and non-availability of d orbitals. Because they cannot have their octet expanded. At max, they can only make maximum 4 bonds, right? So with this, we finish this chapter, okay? So periodic table is complete and new chapter starting from the new day only. Okay. You people revise all these things and whatever is the confusion, you can clarify it, okay? Fine, and do revise because the thing, this particular chapter, and in fact you must read NCERT along with the notes which I have given you, right? So that will be sufficient, and whatever is the model which is there with you, please solve it, okay? So that will be helpful for you, okay? Thank you and have a nice day.